Okay, so hi everybody. My name is Brian Northan. I'm from True North Intelligent Algorithms LLC. And that's just my sort of one-man show consulting company. And today I'm going to talk about flexible deconvolution using ImageJ ops. So just a bit of background how I got into this. I discovered, I've known about ImageJ for a long time, but I really discovered a lot more about it about 2 or 3 years ago when I was looking for a good FFT library, and I stumbled upon ImageLib2, and started asking questions on the listserv and got a lot of help and found it really useful. And then a short time after that, these guys started a project called ImageJ Ops. So what I do is I usually do projects that involve, first of all, verifying measurements. Second of all, making a measurement system easy to use. So I tend to do these niche projects, but I end up with a lot of code that would be reusable for other projects. But what I need is like a way to organize it and to make it reusable. So this ImageJ Ops project, Curtis mentioned it yesterday, and we're going to do a tutorial in it later on. It's just sort of a really, really good architecture for reusing code and making it easy for others to use. So it's really, really useful for me, to when I do a project, sometimes aspects of it are proprietary, but I end up having a lot of general stuff that I need a way to organize, and ops accomplishes that. So in these measurement projects, one of the steps in sort of the pipeline is something called deconvolution. For the last year or so, I've been contributing some deconvolution ops. So I'm going to talk today about deconvolution, explain what it is, some of the problems we face when doing deconvolution, talk about what we've done so far in ops, and then talk about some future goals, and also show some preliminary results. So the very first thing that you really need to think about when you do deconvolution is something called the point spread function. And that basically describes the response of an imaging system to a point-like object. And that's really, really important. If you have the wrong point spread function, your deconvolution will never work. So it's going to be really important to implement a point spread function, good point spread function routines into ops. And that hasn't been done yet. I've looked at a couple of options. I have some links here. There's a nice library called Cosmos, which is a C++ library. It's a very open library, so it's great to use. There's also a utility already in Fiji called PSF Generator, which is another great tool. It's just harder to reuse the code from that. And there's also some things in ICI. So one of the near-term goals of ops is to get this point spread function in there. And that's important because when we image, the blur is defined by the point spread function. So you image, this is a simulated sphere, you image it, and it's blurry. And to understand the nature of the blur, we need these point spread functions. So another thing that's really important when we're doing deconvolution is to consider the noise. So we have our objects, they get blurry, and if this was all that happened, the problem would actually be not that difficult to solve. But in reality, we also have noise. So as I just said, if there was no noise, it would be really easy to solve this equation. If you're familiar with Fourier transforms, you can invert a convolution using frequency domain techniques. But people have looked at this problem for a long time, and the problem with just using the easy way is that you get this noise amplification. So researchers have found that some of the best approaches are iterative approaches. So instead of solving the equation all at once, you do it in steps. And a technique that's been used a long time for deconvolution is something called Richardson Lucy. And I'll show it in pictures instead of an equation. So you have you have your object, it's blurry, and at each iteration, the Richardson Lucy algorithm removes some of the blur. And you keep on doing this. I've sort of shown, these are like iteration 10, 20, 30. So usually, you can't just do it in 3 iterations. You need lots of iterations. Now, there's still a problem when you apply Richardson Lucy to real data. So you have some kind of noisy data. You try to deconvolve it. It removes the blur, but you still get noise artifacts. So researchers, this is another problem that people have been spending years on, and there's a lot of really nice solutions out there for it. But if you are hearing people, when you hear people talk on like the confocal listserv and stuff about deconvolution, they'll often use a term called regularization, and that's just a way of saying the solution is modified to better handle noise. So so this is our so this is our sphere, our noisy sphere. So remember a few slides ago I showed the deconvolution result with just Richardson Lucy. If you use the regularized version, you get a much nicer result. It's also important to discover, consider boundary conditions, because weird things can happen with objects near the edges because there's no pixels to do some of these calculations. So that's something that we're going to have to consider in ops. I don't have time to talk about it in detail today, but I just put a link to a possible approach to solve that problem. Then another really important aspect is the speed, because if you've used this software, even some of the good commercial software takes a really long time to run. So there's a couple of ways that we can make it faster. We can do what's called algorithm acceleration, which means we actually modify the equation. We have this iterative optimization problem, so we sort of take bigger steps at each stage. So hopefully we can solve the problem in fewer steps. And I put a link to another nice approach. And then there's hardware acceleration, which is basically just making the math run faster. And if you could do this, it'll help everything. So it's really good to have fast math libraries to really optimize the multi-threading, and also GPU is an approach people have been looking at. So the current status is we have this Richardson Lucy and Richardson Lucy total variation algorithm implemented in ops. I've also been looking at vector acceleration and an edge handling scheme. And then the future goals are to optimize memory and speed, implement this diffraction-based PSF. There's some really nice algorithms in ICE, which I'd like to look at and possibly implement into ops, and a huge library of phantoms for testing would be good. So here's some preliminary results. This is a publicly available data set by, I think, George McNamara, a frequent poster on the confocal list, put it out there. So I processed this result. Unfortunately, I had to use PSF generator for the PSF, so I've just put a screenshot so I could convey the parameters I used, if anybody wants to try to reproduce this. Then I had just a quick macro to do some centering. And then this is the actual ops code. And we'll be talking a lot more about this afternoon, or actually in about an hour. And so this is what you're looking at here, are ZY projections of some point-like objects that are blurred, and then they're deconvolved. And that was done using ops. It's always good to look at line profiles of these things. That's sort of the original image, and then after you deconvolve, you get much sharper, smoother result. And then again, this is another test object, another object in the test set, and this is XY view before and after deconvolution, and the ZY view. And I'd like to thank these 4 guys, because basically since I've been getting involved in this code, any question I have is answered very, very well by them. And then they've been thanked in a ton of presentations, but just thank them again. So that's it.